In the previous part of this lesson, we evaluated some different arctangent and inverse trig functions, and now we're going to continue to do this, except they'll be more variable in nature, but we're still evaluating. Here we have the cosine of the inverse sine of x. Now, it seems hard to, at first glance, to evaluate this because we have a variable instead of a number, but the principle is still the same. The inverse sine of x is just some angle, and we know something about that angle. We know that its sine value is x, which means its opposite, if theta is here, its opposite is x, and its hypotenuse has to be 1. And since I want to know the cosine of that angle, if I knew what the adjacent would be, I'd be able to solve that. Well, by the Pythagorean theorem, what I want to know squared plus x squared has to equal 1 squared. Or what I want to know squared should equal 1 minus x squared, or what I want to know has to equal the square root of 1 minus x squared. So the answer to my question is simply the square root of 1 minus x squared. Let's try another problem like this. We'd like to evaluate what is the tangent of the inverse cosine of x. Well, again, the inverse cosine of x is just some angle, and what I know about that angle is that its cosine is x, which means that its adjacent must be x, and its hypotenuse must be 1. And when I solve this for the opposite side, I'm going to end up with the square root of 1 minus x squared again. Since I want to know the tangent is just the opposite over the adjacent, so in this case, the opposite over the adjacent would be the square root of 1 minus x squared divided by x. A third example of this type would be, we'd like to know the sine of the inverse cosine of 2x. Well, the inverse cosine of 2x is just some angle, and what I know about that angle is that its cosine value is 2x, which means its adjacent must be 2x and its hypotenuse must be 1. What I want to know has to be related via the Pythagorean theorem, that 2x squared plus what I want to know squared must equal 1 squared, or what I want to know squared has to equal 1 minus 4x squared, or what I want to know is the square root of 1 minus 4x squared. Now that I know what that adjacent side is, or opposite side is, I can figure out the sine of this angle, because the sine is just the opposite over the hypotenuse. So in this case, it would be the square root of 1 minus 4x squared. The final example of this type is, we'd like to know the sine of the inverse tangent, or the arctangent, of 3x. Well, again, the same principle applies. The inverse tangent of 3x is just some angle. What I know about that angle is the opposite over the adjacent is 3x. And what I want to know is the hypotenuse. I need the hypotenuse to find the sine. So 1 squared plus 3x squared must equal what I want to know squared. 1 plus 9x squared must equal what I want to know squared, so its square root is what I want to know. Now that I know that, I can make a statement about the sine value, since sine is opposite 3x over hypotenuse, the square root of 1 plus 9x squared. And I'm going to leave it like that. If it bothers you, you can rationalize it yourself, and you rationalize again by multiplying top and bottom by, in this case, 1 plus 9x squared, the square root of both, if you need to rationalize it. The reason we go through all this is now you're actually able to take the derivative of inverse sine and inverse cosine and inverse tangent, even if you never have them memorized. So let's set that up. So we'd like to find the derivative of the inverse sine of x. We don't yet know what it is. But we do know this. If y is the inverse sine of x, then the sine of y must equal x. Right? That has to follow. And if the sine of y equals x, that means if we drew a picture of it, a couple things. It means that if our angle is y, then its sine is x, so the opposite of it must be x, and the adjacent to it must, or the hypotenuse must be 1. And if we use the Pythagorean theorem, then we'll find that the adjacent side must be 1 minus x squared. Right? Well, this is really helpful for us, because if we deal with the sine of y being equal to x and took the derivative of both sides, using implicit differentiation, the derivative of sine y is the cosine of y times dy dx, and the derivative of x is just 1. And if we solve for dy dx, we end up with 1 over the cosine of y. But now if we go back to our picture, we know that the cosine of y is just the adjacent over the hypotenuse, or the square root of 1 minus x squared over 1. So the derivative is 1 over the square root of 1 minus x squared. And we've just demonstrated a proof for what the derivative of the inverse sine function is, just by using some basic facts that we already had. Right? So you don't even need to memorize this if you don't want to, although it can be helpful, because now you could be able to derive it, and you should be able to derive the other two yourself now. So I would encourage you to pause the video and see if you can derive both what's the derivative of the inverse cosine of x, using what we did as a model, and what is the derivative of the inverse tangent of x. Now, if you're checking your work, the derivative of y equals the inverse cosine of x. Well, what we do know is that the cosine of y has to equal x. So a picture of that means that if my angle is y, then the cosine is the adjacent over the hypotenuse. And if I were to solve that for the opposite side, I'm going to end up with the square root of 1 minus x squared again. If I use implicit differentiation to take to the derivative of cosine y equals x, we'll end up with negative sine y dy dx equals 1, which means that dy dx equals negative 1 over the sine of y. And we can figure out the sine of y from our picture. Since the sine of y is the opposite over the hypotenuse, I would have negative 1 over the square root of 1 minus x squared. Finally, if we're going to consider, I'll do this below, the derivative of the inverse tangent of x. Using the same problem as a model, this means that the tangent of y should equal x, which means in terms of a picture, if y is the angle, then the opposite over the adjacent is equal to x, and if we solved for the hypotenuse, we would get that the hypotenuse equals the square root of x squared plus 1. Well, now using implicit differentiation on the tangent of y, what we'll get is secant squared y dy dx equals 1. Recall that secant y is the same as 1 over cosine y. So this is 1 over the cosine squared of y times dy dx equals 1, or dy dx must equal the cosine of y squared, or cosine squared y. Well, the cosine of y is the adjacent over the hypotenuse, so that would be 1 over the square root of x squared plus 1 squared, and when you square that, we end up with 1 over x squared plus 1. So we've just derived all of the derivatives of all of the inverse trig functions. Extending this one step further, if we were going to take the derivative of the inverse sine instead of x of u, so instead of x we've got something a little more complicated, then all we've got to recall is just the chain rule, that the derivative would be 1 over the square root of 1 minus u squared times du dx. And the derivative of inverse cosine and inverse tangent, if the variable piece is more complicated than just x, is going to be the same thing. For inverse cosine, it would be negative 1 over the square root of 1 minus u squared times du dx by the chain rule. And for inverse tangent, it'll be 1 over 1 plus u squared times du dx. So let's practice applying these rules. What is the derivative of the inverse sine of 4x? Well, I know that the derivative of the inverse sine is 1 over the square root of 1 minus, it'll be 4x squared, so 16x squared in this case, times du dx, which will be 4 in this case. Or I could write the 4 in the numerator, which personally I would prefer. What about y equals the inverse tangent of x cubed? Well, the derivative of inverse tangent is 1 over 1 plus the quantity squared, so x cubed squared would be x to the 6th, times the derivative of x cubed would be times 3x squared, and that'll end up in the numerator. Another example, same idea. Y equals the quantity, the inverse cosine of x over 2 cubed. What's the derivative? Well, here we can start with the power rule, and then we'll just use the chain rule a bunch. So by the power rule, we'll have 3 times the inverse cosine of x over 2 squared times the derivative of the inside. Well, the derivative of inverse cosine is negative 1 over the square root of 1 minus, it'll be x over 2 squared, so 1/4 x squared times the derivative of x over 2, which is 1/2, and we can clean that up at another time. Final example of this type here in our lesson will be y equals x times the inverse sine, or the arcsine of x, plus the square root of 1 minus x squared. Right? Well, maybe a couple of weeks ago this would have seemed like a big deal, but here we're just using the product rule on the first part, so that'll be 1 times the inverse sine of x plus x times the derivative of inverse sine is 1 over the square root of 1 minus x squared, plus, recall that the square root of 1 minus x squared is the same thing to the 1/2, so if we use the power rule and the chain rule, we'll have 1/2 times 1 minus x squared to the negative 1/2 times negative 2x, and it's going to really bother me if I don't clean this up, so I'll rewrite this as the inverse sine of x plus x over the square root of 1 minus x squared minus x over the square root of 1 minus x squared, and since all that stuff cancels out, we're left with just the inverse sine of x. So we've got one more example, and there's no point in making another video for it, so we'll finish that here. In this problem, there's an officer in a patrol car, and it's sitting 100 feet away from a highway, and this policeman sees a truck approaching. At some time t, the truck is x feet down the road. The line of sight to the truck makes an angle of theta radians to a perpendicular line to the road, and we have a picture illustrating this. So first we'd like to express theta as an inverse trig function. So how do we relate theta as an inverse trig function? Well, so what we know is the truck to the patrol car is x, and the distance from the patrol car to the highway is 100, and that is relative to theta, opposite and adjacent. So theta is equal to the inverse tangent of the opposite over the adjacent of x over 100. Part B, we'd like to find d theta dt. So this just means that we're taking the derivative of the whole thing with respect to t. So the derivative of arctangent is going to be 1 over 1 plus x over 100 squared. By the chain rule, we'll need to multiply that by 1 over 100. And since we took the derivative of x and not t, we have to remember that we'll have dx dt in this. And we can clean this up a little bit. This will end up being 1 over 1 plus x squared over 100 squared, and all of that is times 100 dx dt. Finally, cleaning it up a little bit more, we'll end up with a denominator of 1 over 100 plus x squared over 100 dx dt. Finally, we could just multiply numerator and denominator by 100 to make this 100 over 10,000 plus x squared dx dt. Now the last part of the question is, when the truck is at x equals 500 feet, the angle is observed to be changing at a rate of, so d theta dt is negative 2 degrees per second. And the question then is, how fast is the car going in feet per second and miles per hour? So a couple things. This angle is not real helpful because it's degrees. So negative 2 degrees per second needs to be converted to radians. And so to convert to radians, I'm going to multiply by pi radians over 180 degrees, which means that I'll have pi 90ths, so negative pi 90ths radians per second. I need to make that conversion because those are the algebraic units that we've been working in, right? And the original problem told us that theta was in radians, so those are the units we're working in. Now I can make some substitutions into d theta dt. So we're told that d theta dt is negative pi 90ths, and that's radians per second. And that is going to be equal to 100 over 10,000 times x squared. And we're told that x in this case is 500 feet. So plus 500 squared times dx dt. And 500 was in terms of feet. So if we solve for dx dt, we should have the change in feet per second. So solving for dx dt, we'll find that it is negative 90.757 feet per second, right? So I've done all the algebra, and I've ended up with this for feet per second. And the negative just has to do with the direction of travel. That's the change in the distance, right? So x is shrinking because the truck is going to the right. Finally, convert this to miles per hour. This is 61.880 miles per hour. So there's a problem involving inverse trig and some derivatives.